Professor Nikhil Pal is a professor in the Electronics and Communication Sciences Unit of the Indian Statistical Institute. His current research interests include bioinformatics, brain science, fuzzy logic, image and pattern analysis, neural networks, and evolutionary computation. He was the editor-in-chief of the IEEE Transactions on Fuzzy Systems for the period January 2005 to December 2010. He is on the editorial boards of several journals, including the International Journal of Approximate Reasoning, Applied Soft Computing, Neural Information Processing, Letters and Reviews, International Journal of Knowledge-Based Intelligent Engineering Systems, International Journal of Neural Systems, Fuzzy Sets and Systems, International Journal of Intelligent Computing in Medical Sciences and Image Processing, International Journal of Uncertainty, Fuzziness and Knowledge-Based Systems, Fuzzy Information and Engineering, and International Journal, and the IEEE Transactions on Systems, Man and Cybernetics B. He has delivered several plenary and keynote talks in different premier international conferences in the area of computational intelligence. He has served as a general chair, program chair, and co-program chair of several international conferences. He is the general chair of Fuzz IEEE 2030.
Thank you. This is what I'm going to talk about. To motivate what I'm going to talk about, I would like to just mention quickly some of the problems that we have worked on really in ISI. For example, prediction of ground vibration from rock materials and the rocks and the blasting material. Because suppose you want to make a tunnel and you want to blast the rocks and you want to make sure that the building do not collapse. Or in West Bengal, jute used to be a very important agricultural product, and often in jute mills, they produce the final yarn and they are not of the right quality, so everything is scrapped. So can we predict, based on the raw jute attributes as well as the machine characteristics, what would be the outcome at the end of the day? Land cover classification from satellite images is kind of, you take satellite picture and you basically try to find out the different types of land coverings, land, water bodies, vegetation, concrete structures. It has both good use and bad uses. If you want to estimate the damage caused by a natural disaster, you use this. If you want to destroy buildings, you also can use it. Our objective was, of course, not a bad one. Detection of microcalcification from mammograms. These are really X-ray images of breast, and you have tiny little bright spots, whether you can do automatic detection. Detection of bounded weak echo region for prediction of severe weather. For this problem, the actual science is not known to me because we collaborated with some group in NOAA in US. So you try to find out some special kind of signature in the radar scan, which indicates that severe weather phenomena is going to come. So there are many more problems. Now these problems apparently look different, but actually in my view, from pattern recognition point of view, they are the same problem. They are tied by a common thread. And what is that? If you like to call, you can call designing intelligent systems, where you are given some input-output data X and Y, and there is an unknown system, and you want to somehow model this unknown system given the data. Normally what we do is we use part of the data to design the system. Sometimes we use part to validate, and then we test it on some unknown data. If we get good results, we are happy, but nobody knows whether they are really a good system or not. So we often try to get some desirable properties in such systems so that we can trust it more. So when you design a system from data, among many other desirable characteristics, some of the things that, at least one of the things the system should have is, it should use adequate, I'm not using the word minimum, adequate information for various reasons. What I'm trying to say is that it should not use, if you have a lot of information, the goal is not to use whatever you have. So you try to use not just the bare minimum, maybe the minimum with some level of redundancy. The reason is if you use just the minimum, if you make a mistake in the measurement stage, your system will fail. So keeping little redundancy is good, but too much redundancy is not good. Now, you may call it that honoring the principle of minimum description length, because you use less number of features, for example, then your system will have less degrees of freedom. If it has a less degrees of freedom, you are likely to get a better system, a system with a better generalization. So this suggests that use of less features or dimensionality reduction, or at a higher level we can call feature analysis, is very important when you are designing a system from data. Now, many features are not necessarily good. It involves more computation, more space, more cost. Cost may be decision making, cost may be design. More free variables means more degrees of freedom. Confusing variables you may have, and it may lead to poor generalization. So the goal would be to eliminate the bad features and also control the use of redundant features, and if needed, you generate new ones. Now, I want to emphasize here one thing. Often people do feature analysis as a separate phase from system design, but we do not like that because it depends on the tool that you are using and also the problem you are trying to solve, because data, tool, and problem, they interact together. Now, in feature analysis, there are typically 4 tasks. One is generation of additional features. If you want, you may rank the features, which is not a good way of handling the problem, because 2 correlated useful features may get very high ranks when you do not need both of them. You can generate a lower dimensional representation of a whole set of features, which often we call feature extraction, and selection of a useful subset of a given set of features. And in today's talk, I will focus on these two ones, the generation of a lower dimensional representation using new features and selection of a useful subset of features. You can think of it as a mapping from p-dimensional to q-dimensional. Typically, p is greater than or equal to q, but not necessarily. For example, if you have an image, you cannot just give the image to the computer for decision making. You have to extract features, so you generate more there. So this is the generally feature analysis. And the process could be a linear or a non-linear one. Like when you do principal component analysis, it's a linear one. What I'm going to talk about is a non-linear one. It could be supervised or unsupervised. In a supervised framework, usually you have a target application in mind, so you can control the process. It's a better way of dealing with the problem, whereas unsupervised way, you do not have any target application with you. So it's more difficult. So the first one is a very simple scheme, which is an unsupervised one, nonlinear dimensionality reduction through feature extraction. I put a question mark after unsupervised because in the traditional sense of supervised learning, where there is a teacher which provides you some target, we don't use that. But in the process, we'll have something like a supervised learning also. So what is the scenario? The scenario is we are given a set of inputs, like set of vectors, feature vectors, xi, which are in p dimension, and we want to find a set of yi's, which are in a lower dimension, such that y captures, quote unquote, the inherent structures of x. Now, really, do I know what I mean by the inherent structure? No, I don't know. But I can give you some example. Like if I have in 3D couple of spheres, the data, and if I want to reduce it in 2D, then I would be happy to get some disks. So what I am trying to say is that if we can maintain the cluster structures, for example, in higher dimension to the lower dimensional representation, we can call it a good criteria. But this is not necessarily the only criteria. So what would be a good criteria? Now, one way would be to preserve the interpoint distances. Now, this is not something that I am proposing. This was done long time back, Salmons. This is what is called one of the ways of doing multidimensional scaling, where we try to preserve the interpoint distances in the high dimensional space to the lower dimensional space. So we are given this x, so we can compute the Euclidean distance. So we can compute the Euclidean distance between pair of vectors, and we want to find a set of yi's which are not known to me, and if we have some initial values, we can compute the interpoint distances between pair of such vectors, and then we minimize an error function of this kind. So this is the distance in the original space, this is the distance in the reduced space, which is kind of scaled down by the distance in the original space. If you do that, then the impact of outlier would be low. And here is one term. Actually, this has got nothing to do with the optimization process because this is a constant given a data set. But I have kept it because in the original Salmons paper it is there and everybody keeps it. But you really don't need this one. Okay. So what you can do is you just simply make some random guess for these yi's. You compute this error and you minimize this error using gradient descent. Apparently you may feel, will it really work? But actually it works great as long as the data set size is not very, very big. Now, a few remarks on this method. First of all, it works great for small data sets. It takes too much of time if it's a large data set, and there are too many free variables because if you have, say, 1 million data points, and if you're reducing to two-dimensional space, so then you have to find out 2 million values of 2 million variables. So this is computationally also very difficult, and if the size is very big, you get stuck to local minima. Of course, gradient descent will always do it. And one of the problem with this, you cannot project a new data point. So you run it, some new data comes, you have to run the entire process using the whole data set again. So question is, and for large data set, this is not a feasible approach. So can we address some of these issues using neural networks? Well, my answer is yes, as far as these three issues are concerned. Too many free variables, we can probably minimize that. Projection of new data points, which is most important attribute, I would say. And for large data sets also, it becomes a feasible process. So what do we do? The basic idea is very, very simple. So you have this huge data, or to start with, you can use the entire data also, or you sample the data, take a subset of the data, and then you apply the Salmons method to generate the y, the lower dimensional representation. Now you are having x's and y's. Now what you can do is, given x's and y's, assuming that there is a functional relationship between x's and y's, you can use any machine learning tool like neural net, fuzzy rule-based system, or other regression model. Using other regression model has a problem because you have to assume the model, and for this kind of complicated mapping, it's very difficult to do that. But neural net and fuzzy rule-based system can do a wonderful job. Now, the question that may come to, does it really make sense and will it really work? Now, it makes sense from this point of view because we are assuming that since we are talking about prediction, so we are assuming the data are being generated from a time invariant probability distribution. So the future data will follow the trend of the current data. And so if we can learn the hidden relation between the higher dimensional data and the projected data in the future data, it should follow. And it does work, that you will see. And the prediction ability becomes inherent because we are using a neural network or a fuzzy logic system. Now here we are going to talk about a multi-layer perceptor network. Now I have a lot of results. I'm not going to spend time on that. I will only focus on the third data sets, which is fear and shell. So this is a data, you have a three-dimensional sphere, and then surrounded by there is a thin shell. Now imagine you used any linear transformation, you won't be able to separate the sphere and shell in 2D. It's not possible, right? Now what happens if you do use this, this method? Well, the results I am going to show, I am using 50% random sample for designing the system and then predicting the whole set. Now this is one of the results that we got using neural network. So this is the projection of the data using original Sammons method on 2D. And this is one of the results which is produced by neural network. Now of course you know the neural network output depends on the initial condition. Now this is neither the best result nor the worst result that it has produced, because if you run 50 times, maybe 30 times you will get results like this, maybe 10 times you will get better than this, and sometimes you will get a bad local minima, which will be worse result. So it can work, and there are many other results also available in our paper. And we have used a fuzzy systems also that also does a great job here. Now this kind of system is fine. It has an advantage because people use Sammons projection for data visualization, but it has some problems also. First of all, the most important problem is, or most serious problem is, you cannot interpret the features that you are extracting. So if I use it for, say, cancer diagnosis and reduce from 12,000 genes to a two-dimensional feature, no doctor is going to buy that, because you have no clue what those features are. So that's a big problem. And even for data visualization, if we want to use, we will use only 2 or 3 dimension, but it may not be good enough to extract the actual structure of the data. And of course, there is no easy way to fix the value of lower dimensional features unless we have a target application in mind. If we have target problem, we might be able to do that. So next what we switch to is dimensionality reduction through feature selection. Here what we are going to do is, we have, say, for example, in a gene expression data, we have 40,000 genes. And I have samples from, say, 4 different types of cancers. And my goal is to find out some of the genes which can discriminate between the 4 types of, say, cancers. Like we have really worked on 4 childhood cancers. Or the question may be, find the list of genes which are related to the disease. These are 2 different questions. So to make it clear that what we are trying to do, I want to mention about what features should we try to really select. So here is some categorization of my features. First is essential features. I call some feature essential if you cannot solve the problem unless you use them. I call derogatory or bad features. These are the bad guys. They will hinder the learning process, so you must reject them. I have one category called indifferent features, which neither help nor cause trouble. You know, in a class, often you will find a student who comes and sit idle, neither create troubles with the teacher nor even learns anything. So if you keep it in the system, no problem. If you reject it, it's fine, but otherwise it's not a problem. And redundant feature, by redundant feature what I mean is, these are the features, they are good guys, but you do not need all of them. Some of them will be good enough. Now, I use this example which I invented. It's a 4-class problem with 5 features. One is gender code, like male, female, height, weight, eye color, and number of legs. And here are my classes. I have 4 classes. One is male with short height or low weight, which is kind of slim, short, weak male, and weak, strong male. Similarly for the female also. I mean, you may not like these classes and they may not be exhaustive also, but these are the classes of my interest. Now, given that, it's obvious that what is the essential feature? This is gender code. Because if you don't select gender code, you won't be able to solve this problem. So there are features which are essential. Redundant set, height and weight. Given my definitions of classes, we do not need both of them. Only one is good enough. So they form a redundant set, and I can use one of them only. Bad feature, eye color. The classes that I have defined, eye color has got no relation. So if you keep it, it will create trouble during the learning. So I must eliminate this bad guy. And number of legs, unless something has gone wrong for some unfortunate reason, everyone has two. So if we keep it, no problem. If we reject it, no problem. So I just want to make it further clear, does any pair of correlated or dependent features form a redundant pair for our purpose? My answer to that is no. We call it redundant only when they are useful. And can some redundant features be necessary? You have seen already an example, because height and weight, one of them is necessary to solve the problem. So redundant does not exclude, so my classification is not mutually exclusive. Just wanted to make sure it is. So there exists a more general problem, and I motivate it using this example. Actually, we wrote the paper based on this problem. When, for example, I'm trying to design an intelligent weld inspection system, and the purpose of this weld inspection system is maybe to find out cracks on a reactor vessel where human being cannot go, and you don't have too much space. And you know, in a welding inspection system, it has to be done in real time. Because welding, if it becomes solid and if you try to repair, it's not an easy, it doesn't work. So typical sources of information may be radiograph, which are X-ray images, acoustic emission, thermograph, and many other sources. Now, each of these sensors produces, like thermograph produces an image. Now, you have to extract a set of features from there. So each of these sensors produces essentially a set of features. And our goal was there to minimize the number of sensors, not number of features, because you don't have too much processing time. So this is a generalized feature selection problem, where instead of selecting individual features, you select a group of features or reject a group of features. And it has many other applications, and unfortunately when we worked on this, we could not find anything in the literature. This is a current problem that we are working on. We are trying to find out, like, if we make what they call motor imagery action, like I think about I am moving my right hand or left hand, if we can recognize the EEG signal signature corresponding to that, we may be able to design a system which can be used to help people. Now, typically they use this 10-20 system. You have 32 electrodes, so 32 sensors, but all of them are not relevant for your problem. So every channel or every sensor produces, like you can use first Fourier transform or any other transform to produce a lot of features. So from every channel, you produce different numbers of features, and your goal is to find out which channel is good for your application, which is not. So this is a generalized form of feature selection we call sensor selection. So here goal is, as I mentioned, either you accept all features coming from a sensor or you reject all features coming from a sensor. Once you select the sensor, you can go to the feature selection. So the goal here is we want to design a mechanism to discard bad and indifferent feature sensors, control the use of redundant feature sensors to solve the problem at hand satisfactorily. I don't want to use the word optimally. There is, for this kind of problem, it doesn't exist. If satisfactorily, I am happy, I am satisfied. Now, I mentioned at the beginning that often feature selection is done in a separate phase. We say that's not the right way because the tool, the problem, and features, they interact. The features which are the best for solving a problem using support vector machine may not necessarily be the best when you're using, say, nearest neighbor classifier. So the solution would be an integrated approach where you try to solve the main problem, and while trying to solve the main problem, you pick up whatever is needed and discard whatever is not needed. So that's the philosophy we are going to use. And we have two solutions. One is using radial basis function network. One is using multilayer perceptron network. I will spend more time on one of them. The other would be obvious then. Okay. So this is an architecture for a radial basis function network. Okay. So here, this is the input layer. Here all features are supplied. I show here 3, there could be hundreds and thousands. And the second layer, what it does is it computes, the phi function is outside my screen. So it computes a function which is kind of a Gaussian hat type of function. And you can see x is in p dimension, and then this node is connected to all p input nodes. And therefore, all these connections can be viewed as a vector in p dimension, and that's what I call Mi. I don't like to use equations in the talk, but sometimes it's just unavoidable. So it's kind of a Gaussian hat you are putting here. So if the input x is close to Mi, you will get a higher response. And then this, at the next level, what you do is you compute and weighted sum of this response from the previous level. So again, all this weighted sum, you can see that. And then finally, when you are given some input-output data, what you call training data, you just minimize the system error. So you use some mechanism to initialize the network. I'll talk about how you can do it in a very simple manner. And then you supply the input, compute the output. This is the computed output, and this is the target output. And you minimize the error. Typically, we use gradient descent, but you can use any other method to do that. Now, I am going to make slight modification of this architecture. And it's, again, school-level algebra. So what you see is that we had at this node x minus mi norm of that, Euclidean norm of that, and we just write that as a product of p component functions, which is just simply because it's an exponential function, so you can do that. And this will have an advantage for us. And we also make some change in the second layer. Instead of just a linear sum, we are using a sigmoidal function. This is just for convenience, because some of the applications are classification applications where the class outputs are 0 or 1. If I use linear sum, learning becomes difficult, so we use this transformation. And finally, the same error function is being minimized. Now, if I assume that there are L sensors, so my input vector x is really composed of S subvectors, one vector from one sensor, and that's I denote here S1, S2, SL. So the whole thing is this concatenated vector is in p dimension. And the weight vector Mi also we can think of as consisting of L subvectors. And then what I can do, I can write down again this activation function of this RBF node as a product of kind of sensory basis function. So here what I am using is instead of x, I am using the input coming from one sensor, and then this is the vector corresponding to weight vector corresponding to that sensor. Now this is the most important part here. Now if a sensor is bad, what I want? I do not want the effect of that sensor to be propagated upwards. and if it is good, I want to keep it unaltered. So how can I do that? If by some mechanism for bad sensor, I can make this value equal to 1, then this will not have any effect down the road. So the goal is devise a mechanism so that for bad sensor, I can make this e to the power, this whole thing, the sensory basis function value equal to 1, and for good sensor, I want to keep it unaltered. So if I can do it, my problem is solved. So what is the main philosophy here? I'll give an analogy. Say I want to solve a problem in this room, and this room has, I see 5 or 6 doors. So they are, I call them as sensors, and behind each door there are a set of people. Behind every door, they are the features. Now my goal is, if I find behind this door there are some people who can help me solve the problem, I'll open the door, allow them in. If I find the people behind the door is not good, they can create trouble for me, I will close the door, keep it permanently closed. So that's precisely what I'm going to do here. So I need, now again to realize this, you see if I keep the door completely closed, I cannot do it. So I need to keep the door little open and ask some questions to the people who are on the other side. And if I'm happy with the answer, I open it. If I'm more happy, asking more questions, I open it completely. So that's precisely what I'm going to do here. So we need to model the doors and a way to decide who should be opened and who should be closed. This is a pictorial representation of this gate. So that's with every sensor we put a gate here. This I have already mentioned. So this is my sensory basis function. Now this is, we make a slight change to this. What is the change? I just simply raise the whole thing to the power gamma j, where this basis function correspond to the jth sensor. Now this simple trick helps me, because if I can somehow set gamma j to 0, then this quantity becomes 1. So I want to set gamma j equal to 0 for bad sensors, but I still do not know who is bad. And if gamma j equal to 1, then this output remains unaltered. So for good sensor, I want to set gamma j equal to 1. Now I do a little more trick here. I replace gamma j by 1 minus e to the power minus beta j square. Now why am I doing it? Again, just for mathematical convenience, because I'm going to use gradient descent. Now even if I start with a value between 0 and 1, gradient descent will not ensure that when I finish it, it will lie between 0 and 1. But if I use this transformation, then irrespective of the value of beta j, positive or negative, this will lie between 0 and 1. So now if beta j, the absolute value of beta j is close to 0, then of course this becomes the sensory basis function output is close to 1, it's a poor sensor. And if it is infinity or very high, then it becomes 1, so it's a good sensor. So now my learning philosophy is very simple. So initialize beta j to a value so that every sensors are bad. And then I have system error. So I use gradient descent, start reducing the error. And what happens, the sensor which can reduce the error faster, the beta corresponding to that sensor will be open faster, and that gate will be open faster. So after some time, when my error is satisfactory, I stop my training, look at the beta values, and pick up the sensors which are good or which are bad. Well, this is here I am trying to explain how you can initialize the network. A simple way would be you just cluster your data. Every cluster will give you, like using k-means or fuzzy c-means. Every cluster will give you a cluster center. So you can use the cluster center to initialize the AMIs. And the spread, there are many ways to set the spreads. In my experiments, what we did is we consider one cluster center and find out the closest one and take the distance. There are many ways you can set them, you can tune them, but we didn't do any tuning of these initial centers and as well as the spread. Even then, our job is done. This I skip. How do I threshold it? I think those are the details which can be skipped. Now, if we go to the multilayer perceptron network, it is the same door concept I am going to use, but the trick is slightly different. And you will get it immediately. Again, this is a layered architecture, as you can see. So you supply the input here. Now here, every node makes a weighted sum of the inputs and then apply a sigmoidal transformation. These nodes, everybody does same kind of operation, and there are complete connections between layers and no connection within a layer, and the input layer is simply the fan-out layer. Now, here, so if I look at the function at this node, so this, as you can see, that if we have P inputs, so this node is connected with P weights, so you compute weighted sum of the inputs, which is called the net. So this is the sum of all P inputs, which are coming from really L sensors, and after that you produce, you apply a sigmoidal function. Now you can easily write down, if you have L sensors, then you can easily write down that net is equal to sum of L sensory nets. So now previous one was product, but here it is sum. So if I want to eliminate the effect of a bad sensor, what should I do? Since this is a sum, I should set the sum to 0. Then it should have no effect. I don't have to care about the remaining layers of the network. So for bad sensor, my goal would be set to the net corresponding to that sensor to be 0, and for good sensor, it should remain as it is. So for this, the modeling of the gates, we don't raise to the power anything, but these are multiplicative. So we have this gate, somehow we will model the gate value will lie between 0 and 1, depending on whether it's a good or bad, and for all features coming from a sensor, we multiply it by the sensory gates, sensory gate values. So what could be the modeling of the gates? This is again a pictorial representation of the same thing. Now you can use a sigmoidal function, and as you can see that here, if you have a large negative beta I, then the product becomes 0, so gate is closed. And if you have a large positive beta I, then the f beta I, the gate function is nearly 1, and therefore the gate is open, all features gets into the network. You can use other functions also, like e to the power minus beta L square also you can use. And the learning procedure, nothing changes. Depending on how you model the gate, you set the parameter of the beta so that gates are almost closed at the beginning of the training. Now, if you close it completely, the learning cannot proceed. So this is a key thing here. And then you just use gradient descent to learn it. We have lots of results. I just want to focus on maybe 2 results. This is a very well-known but simple data sets on a chemical plant where this is from this famous guy Sugeno. He wrote a paper in the first issue of IEEE Transactions on fuzzy systems. So you have 5 inputs, which are monomer concentration, change of monomer concentration, monomer flow rate, and 2 temperatures. And your output is the set point for the monomer flow rate, and you have only about 70-75 points for this data set. And it is known, many people have worked on this problem, and people have found that these 2 temperatures are not important. and the others are important. Now you can have a natural grouping here, U1, U2, so we consider this is coming from, these two are coming from one sensor, these two are coming from one sensor, and this is the third sensor. If we use the RBF frameworks, then what we find is, we find that the group 2, the sensor 2 is important and others are not important. When I saw that result, we were kind of surprised, shocked, not happy. When we looked at the output was good, but not happy because the author who introduced the data, he said that the other group is also important. So we tried to look at why it's happening. So when we looked at the detail, we found that the feature 3, which we selected, had a correlation with the output as 0.9998. This is the exact value. So which means basically one can say the other with a very high accuracy. And also if you look at the data variances, then this third feature changes from 401 to 7000, the output changes from 500 to 7000, whereas for all other features they have very small magnitudes. And we are using basis function with Euclidean distance, so this guy dominated. So if our analysis is correct, then if we normalize the data, the problem would be solved. So we normalize the data and the problem indeed solved. But still we need to be careful here about the values. It says they are important but not very important. Now I skipped some slides where I have explained how you choose who is good, who is bad. So there we come up with a threshold. So this is above the threshold, so we select it. Interesting thing is if you go to neural network, and it says both of them are very, very important, while the third one is not. So this emphasizes the relevance of a feature or a sensor is a function of the tool also. I'll just go with one more data, which is iris data. Now, this is a data which is a very simple data. This is on 3 kinds of flowers, 4-dimensional data. In pattern recognition, it's very well known. If you don't use the data, referees will say, why didn't you use the iris data? Because we know it so well, we can understand what is going on. And if you use it and explain the result, then they will say, hey, this is a trivial toy data. Why did you use it? So people know it very well. And you can see if you look at the features, so there are 2 natural groups. You can assume each individual feature also as a group. Then you can get feature selection using this method. And you can have this natural grouping also. And in the pattern recognition community, the belief is that these 2 features, these 2 petal length and petal width, are the most important ones, which is true. But feature 1 also has a very high correlation with these 2. So which means feature 1 also has a substantial amount of discriminating power. So if I use this data set, if I use RBF, and if I assume every feature is a sensor, so it's said group 4 as the most important, which everybody is happy with, and group 3 is the next most important, and it rejects group 1 and group 2. Now, by the way, I must mention that when you use individual feature, most of the time you get these 2. Sometimes you can get this guy also important. The reason is it has a very strong correlation with others. And if I use 2 features as a group, it considers the second group as the most important and rejects the first one. For multi-layer perceptron, I just show here a picture to just point out some limitation of the method. So this is when you use 2 groups, say around iteration number 1500, so misclassification drops because the second gate opens, and if you continue training, what happens is after some time the other gate also opens and the misclassification goes down significantly. The reason I show this, I want to emphasize, we are using gradient descent, and if some feature has some discriminating power, if we continue the training, it can pick up them also, because I did not penalize for redundancy. So that's a limitation of this method. So I just want to emphasize on this, who will get selected, because I classified the features. First of all, my claim is essential features will be selected. Now, we are using gradient descent. It could be a bad local minima. You know that looking at the total square error, if it's a bad run, you reject it. So if your square error is acceptable, then essential features are selected. What about indifferent features? Will they be selected? My answer is no, because initially you keep the gate closed. It cannot reduce the error, so it will not get opened. And for redundant features, well, more than one redundant features may get selected because we did not penalize for redundancy. That's a weakness of this method. And if we treat every feature as a sensor, we get feature selection. Well, summary is the usual one, so to keep some time for questions, I just want to emphasize for the last one. When we wrote this paper, we didn't have a solution how to control the redundancy. Actually, in most of the times, it does not pick up too many redundant ones. But if you repeat the run, say 100 times, then if you look at the set, you do get redundant ones. So now we have a solutions to how to control the redundancy. We're just writing up the paper, which is simply adding a penalty for redundancy in the learning process. With this, thank you very much.